So on this worksheet, you need to roll a dice 60 times and flip a coin 50 times. And for the dice, we are recording how many fives and not fives you get. And then for the penny, we are recording heads and tails. So if I roll a dice 60 times, let's say that I end up with 12 fives. Okay. So the first question asks, how many times did you roll a 5? 12. So fives make up what percentage of all of your rolls? So 12. Oh, I don't want to do 12, do I? No. Let's do 11. So that's the answer to number 1 for me. And then 11 out of 60. 11 out of 60 is 18.3%. Okay. If the dice were fair, how many fives would you expect to roll in 60 rolls? Well, what does it mean for a dice to be fair? What is an unfair dice? So you could how many fives are there, and don't put any fives on the dice, or maybe put 2 fives. But a fair dice is equally balanced, so every number is equally likely to show up. If we looked at a dice, and when we made the dice, if we made the the edge of the 1 really heavy, then that 1 is really likely to be pointed down, which means 6 would show up more than any other number. So a weighted dice is unfair, meaning it does not have an equal chance of winning. Now, if you go to Vegas or any other casino, they really want fair dice, because with fair dice, certain numbers are not more likely. If the dice is unfair and you notice that, hey, 6 shows up a lot more than the others, then you're going to start betting on 6, and the casino could lose money. So casino dice are very well weighted because they need to be fair. So if the dice were fair, how many fives would you expect to roll? Well, 1 in 6 rolls would be a 5. So I take 1 divided by 6, and then I roll the dice 60 times, and I end up with 10. So the answer to the third question is 10. If the dice were fair, what percentage of the rolls would be fives? That would be 10 out of 60. Or you could say 1 roll in 6. And in both cases, you're going to end up with 16.6%. Okay. In your opinion, is your dice fair? So I made up my rolls, but I got 11 fives. Is my dice weighted appropriately? Well, I didn't get 10. Is that okay? I expect 10. Right? That is my best guess. But am I guaranteed to get 10? No. So we're going to start looking into statistics, and we're going to say, is 11 close enough to 10 that we can say that the dice is fair? Now, what would your guess be? Yes. My dice is probably fair. What if it was 12? That's probably still true. 25? No. Something's wrong. Okay? So the question is, how far off do you have to be before you start saying, no, the dice is not fair? And you want to know the simple answer to that? However close you want. Right? We get to choose whether it's fair or not. Is that a little bit scary? Now, we do follow some rules, and there are some pretty well accepted guidelines, but there really is no reason why you can't change the guideline and say, nope, it's not fair. So it all comes down to how close do you have to be for the dice to still be considered fair. Now, is it possible to roll 60 times and get 65s? Yes, it is possible. Do you think it's going to happen? No. which is why winning the lottery is not worth it. I had a statistics professor in college that used to tell us, remember, we'd be loading up our backpacks, and he'd say, remember, the lottery is a tax on stupid people. So play the lottery if you're stupid. It's essentially like getting 65s in a row. Somebody might get it, but the chance of it is so low that it's not going to happen. So, in my opinion, 11, yes, the dice is fair. What if I only rolled fives? We don't know. I haven't taught you how to tell if it's a yes or a no. But remember, you get to choose how accurate you want to be. And you'll see that in a little bit later. Okay. How many fives did the entire class roll? So here is the information from yesterday. And each one of these is dice, comma, coin. So if you add up all of the dice, what did you get? One what? 219? Okay, and then we have 5, 10, 15, 20, 21. So 219. How many fives should we expect the entire class to roll? It's going to be 21 times 60. So 219 divided by 21 times 60. Okay. Oh wait, that's not what I wanted. So sorry, I wanted 21. 10 times 6. 10 times 21. How about that? There we go. So the class was expected to roll fives 210 times, and they rolled 219 times. Do you think that the class dice are fair? Now, wait a minute. I was off by 1 in the last go around in mine, and the class is off by 9, and you still think they're fair? It's fair? It's a larger set of data, so that's going to be really important in what we do here. Now, if we rolled 19 individually, we were off by 9, would we consider the dice to be fair? Maybe not. 19 is pretty far, but if I take 210 and add 9 to it, because that data set is so much bigger, 9 doesn't mean as much. So you have to look at it in terms of percentages, not absolutes. Okay, and we'll talk a lot about that. So does it appear the dice in the classroom are fair? Yes. We got 219 instead of 210. That's really close. If we looked at that as a percentage, it's 17.3. So the actual percentage should be 16.6, and the class percentage is 17.3. Those are really close. We're within 1%. Okay. Okay. The law of large numbers. So we have dealt with populations thus far. We have measured heights and weights and all sorts of other things of a population. The goal of statistics is to take a sample and use that information to make inferences on the population, because it's just too hard to talk to the population. We don't have enough time, we don't have enough money, people are always dying and getting born, and it's hard to do. So true statistics is the study of samples. And here we've taken a sample. Right? Everybody sampled a dice 60 times. Okay? And what is the population of this? The population would be every possible person rolling every possible dice an infinite number of times. Does that make sense? We don't have that kind of time. So what we're going to look at is the ideal. What do we expect to happen? Well, we already know 1 in 6 sides of the dice is a 5. So we expect 5s 1 out of 6 times. 1 out of 6 rolls. Well, how many rolls are you going to do? And it's all different. So instead of 1 out of 6, we're going to look at it as a percentage. We expect 5s 16.6% of the time. Okay? So there's no way we can roll the dice an infinite number of times, but we expect 16.6% of the rolls to be 5s. Okay? The law of large numbers says if you do a sample many, many, many times, the sample percentage will approach the actual, or in some cases, the expected percentage. So the law of large numbers says, and there are lots of ways to interpret the law of large numbers. This is just one of them. If you sample a lot of times, now how many is a lot? I don't know. It depends. Okay? A lot might be 700. A lot might be 10 million. A lot could be 48 billion. It just depends on what you're doing. But the law of large numbers says the more you sample, the more your percentage will get closer and closer to the actual percentage or the expected percentage. For instance, let's say I wanted to know the average height of all the people in the entire world. That is impossible to find. Okay? But the law of large numbers says if I sample a lot of people, then the average I get will be really close to the true average. Now we have 7.2 or 3 billion people on Earth. How many are you going to have to sample? 1,000, a million, a billion? I don't know. The law of large numbers doesn't say how many you have to do. The law of large numbers says the more you sample, the bigger your sample size, the closer and closer you get to the actual percentage. Now, in dice rolling, there is no actual percentage. But there is an expected percentage, and those are two different things. Okay, an expected percentage is the percentage of dice we expect to have 5s on them. The actual percentage, or we could say the actual average, would be if you measured everybody on Earth and found the average, that's the actual average. So we kind of have two different things to look at. We could play this dice game lots of times, or we could go talk to real people. And there's a difference between actual and expected, although we treat them kind of the same. Does that make sense? But just know the law of large numbers says eventually, if you sample enough, your sample will approach or be equal to the actual or the expected percentage. Okay. Coin flip. I flip coins 50 times. I end up with, not 12, with 22 heads. So my percentage, 22 out of 50, is 44%. Okay, and I'm off by 3. If the penny were fair, how many H's would you expect? We would expect 25, which is where I got this 3 from. In your opinion, is your penny fair? I flipped it 50 times, I got 22 heads. Is my penny fair? It could be. Now notice, we don't say, yes, it's fair. Instead, we say, we don't think it's unfair. Do you see the difference? Is 22 enough to say, yes, the penny is fair? No. But we are pretty sure it's not unfair. Okay? How far away would you have to be before you say it's unfair? 21? 20? 7? If you flipped heads 7 times, would you think it's unfair? Yeah, definitely. So somewhere between 22 and 7 is that magic place where all of a sudden we say, okay, unfair. So we're kind of fair, probably, maybe, might be, probably not, definitely not, there is no way. Okay, there's that big scale in there, and somewhere we have to put the line saying fair or unfair. Okay, and where is that line? We sort of get to choose. Okay. Now you don't flip pennies and you look at it and then you draw the line. What you decide beforehand is how accurate do you want to be? Do you want to be 1% off or 5% off or 10% off? You choose that number and then you flip the penny. And that number will help you draw the line. Okay. And that's kind of where we're headed in statistics. Okay. How many H's did the entire class flip? 509? Oh, 520. Wow. And 21 times 25 is the expected. So we expected 525. Do we think that the coins that the whole class used were fair? Yeah, probably. Now, wait a minute. I was off by 3 and you said yes. And now I'm off by 5 and you still said yes. Is that okay? Yes, because this 5 is actually more accurate than the 3. Why is that? Because we have more flips. Okay, so if we did it in a percentage, I had 22 over 50. My percentage is 0.44, so I'm 6% off, 6 percentage points off. And if we did 520 divided by 525, that one, oh, wait a minute, times 2, huh? So 520 divided by 1050. And now I'm off by less than 0.5%. Okay. Did we expect that to happen? Yes. Because the law of large numbers says the more flips you do, the closer you should get to the expected value. Okay. Now, what is a large number? We don't know. Big number. If it's not big enough, keep going. And if it's not big enough, keep going. All right. That's it.